Aircraft with sudden damage or loss of power often rely on gliding to safely land. Gliding aircraft presents a challenge for autonomous path planning algorithms. The steady dissipation of altitude to maintain the glide means that there is limited access to energy and severely reduced flight range. A path planner must manage and dissipate this energy in a controlled manner in order to safely reach a landing site. Current path planning techniques do not account for the severe restriction in range and energy dissipation for gliding aircraft. Closed-loop prediction allows for an estimate of the remaining energy that can be used as an advanced heuristic for path planning. This research presents a modified version of a rapidly exploring random tree algorithm with closed-loop prediction where nodes that can't reach the goal are pruned from the search tree. This algorithm was demonstrated on an experimental unmanned fixed-wing aircraft, the Zod Drift. A gliding aircraft is limited to dissipating altitude gradually due to drag in order to stay airborne without a source of thrust. Because the aircraft is limited to a controlled descent, altitude is no longer fully controllable and the elevator is primarily used to maintain the velocity of the airplane in the absence of thrust. A glide velocity controller maintains the aircraft at an ideal airspeed that maximizes the lift-to-drag ratio of the aircraft, which maximizes the range the aircraft can fly. Dissipating excess altitude had previously been done for autonomous systems by flying suboptimal paths that take longer to reach the goal. Altitude dissipation could be done more effectively, however, by increasing airspeed. A novel control scheme is proposed that would take advantage of the fact that energy dissipation rate due to drag increases proportionally to the cube of the airspeed. By rapidly increasing the airspeed for a brief period of time, the excess altitude is quickly dissipated and the aircraft can return to the optimal glide velocity for the remainder of the path. The path planner used for this project adds a goal feasibility check before adding a new node to the search tree. It begins each loop iteration by sampling a new node and forward simulating the glide dynamics towards that node. After a collision check, the dynamics are then forward simulated towards the goal to make sure that the aircraft has enough range to reach it. If both checks are passed, the node is added to the search tree. If the goal is reached, then the path is complete. Otherwise, the algorithm continues sampling until a path to the goal is established or the maximum iterations is reached. The modified algorithm was compared to standard closed-loop RRT by running each algorithm 1,000 times with a maximum of 1,000 node samples. The modified glide algorithm achieved a 100% success rate for the test, and the average number of nodes sampled to find a feasible path was only 12.7. This is a drastic improvement over regular closed-loop RRT, which wastes time with gliding aircraft dynamics by expanding branches that could never reach the goal. The final two figures compare the plots of the search trees generated by each algorithm, which gives an idea of how many more nodes that regular closed-loop RRT will often expand compared with closed-loop RRT Glide. These methods were implemented on a custom autonomous fixed-wing platform. A test mission was set up to demonstrate the ability of the planning algorithm on the experimental aircraft. It starts with a manual takeoff, then the aircraft begins following a waypoint mission. At the third waypoint, the aircraft is set to disable the thrust, which triggers the autonomous glide algorithm. The resulting path plan is shown, and the waypoints are uploaded to the drone and also updated in the ground station view. The aircraft then proceeds to glide through each waypoint, and for the final waypoint, it loses the excess altitude it needs to execute a proper landing. After reaching the final waypoint, the aircraft makes a final turn to line up with the desired landing area and gently glides to the ground. The planning result overlaid with the flight path shows how successful the algorithm is. The flight path showed excellent agreement laterally with the predicted flight path, indicating that the dynamics model does a good job representing the actual aircraft during closed-loop simulation. The flight path also successfully avoids the obstacle regions and lands along the runway area as intended. The plot of multiple trials shows more of the results achieved with this path planning architecture and experimental hardware setup. Multiple tests were done with consistently successful glide landings from a loss of thrust event that disrupted the UAV's mission. The robustness shows promise for applications that will reduce the risk associated with a loss of thrust event for future aircraft.